So here we are, ladies and gentlemen, at the Chapter 11 Fix Your Test video cast. You're watching this because you want to improve in your knowledge and understanding of Chapter 11. To fix your Chapter 11 test and to earn a better score, you need to know more. And so, number one, what you need to do is take all of these notes, all of them. You need to take all of them, and you need to take them very neatly. So get out some paper and a pencil, pause the video now, make sure that you have paper and pencil out in front of you that you can write down, because there's 4 solid pages of reteaching of Chapter 11 stuff that you did not know on the test. Or maybe you knew some of it and you need to know more. Step number 2, after you take all the notes, I'm going to go through the test, and I need you to fix each problem that you get wrong. Every problem you got wrong, you have to fix it in this way. Write down the number of the problem that you got wrong, and write down the correct answer. Correct answer for the number of the problem you got wrong. So put the problem number down, and I'll do an example of this. Problem number 1, the correct answer is B, or whatever it is. Then number 2, you have to say why it's wrong. And if you give a real reason why it's wrong, you have to say, well, I didn't know that the intermolecular forces were dipole-dipole, or I didn't know that it was a polar molecule. And it has to be a real reason. It can't just be because I'm not smart. It's got to be you are smart. You have to give the real reason why you got it wrong. And then number 3, you have to say why you're not going to get it wrong in the future. Why are you not going to get it wrong in the future? And for this, what do you know now? Well, I know how to find dipole forces. I know how to know what's polar, what's non-polar, etc. So pause now. Pause the video now. Make sure that you got a paper, pencil, and it helps to have a periodic table out. And then, of course, you got to have your old test out, too. So then you can fix the ones that you got wrong along the way. All right, here we go. Chapter 11 notes, an overview of the whole chapter. Chapter 11 has to do with forces. It has to do with forces between things that compose stuff. And there are 4 main columns, and I want you to take a piece of paper and write these 4 main columns down. There are ionic forces that hold things together, metallic, covalent network, and just straight covalently bonded things in the world. That pretty much comprises 99% of everything else. There are some atomic force things that are together that are just atoms, that are like noble gases, but we're going to ignore those for now because we're going to hit these 4 major areas. And differentiating between these 4 is the key. We're going to go group by group, and I'm going to focus in, first of all, on ionic over here on the left-hand side. Ionically bonded things are things that are composed of metals and nonmetals, metals and polyatomic ions, 2 polyatomic ions, or a polyatomic ion and a nonmetal. You have to recognize that right away, that this is what an ionic thing is. If it's got a metal in it and something else, jump all over this one right away and know it's ionic. Ionic things are held together by what's called lattice energy. Lattice energy is a strong electrostatic force that sticks positive and negatively charged things together. They're attracted to one another. These things need to break. These lattice energy charges need to break to have a phase change happen. And whether the phase change be solid to liquid, liquid to gas, solid to gas, just the evaporation of something or the sublimation of something, doesn't matter. These things need to break. These positive, negative attractions need to break in ionic things. Lattice energy's equation is Q1 times Q2 divided by D. Q1 and Q2 are the charges on the ions, so the bigger the charges, if they're positive 2 and negative 2, that's more charged and therefore a higher lattice energy than positive 1 and negative 1. Divided by D. D is the distance between the ions. So, of course, if you have bigger ions, the lattice energy is smaller. If you have smaller ions, then the lattice energy is bigger. These forces are strong in comparison to a lot of the things that we'll talk about in this chapter. There are ionic bonds. Ionically bonded things take like up to a minimum of 500 degrees Celsius to start to melt them, to go from a solid to a liquid. You know, there's many ionic things that need more than 1,000 degrees Celsius temperature at atmospheric pressure to have them melt. And so they are strongly bonded together. These things do not melt at a low temperature. Identifying and differentiating between everything else, the other 4 types, is key with ionic. Because once you see it's ionic, you know, oh, they stick together really, really good. All right, next, metallically bonded things. Metallically bonded things are held together by metallic bonds. Metallic bonds can be strong, like in titanium. Titanium doesn't melt till over 2,000 Celsius, or they can be relatively just normal, like mercury is a liquid at room temperature. Metallic bonds have a wide range. They are shared electrons that are delocalized. You can't say just because it's metallically bonded that it has a high melting point or a low melting point. You can't say that for sure. You just know that there's these delocalized electrons and that metallic bonds hold metals together. So if you see something that's just a metal on the periodic table and nothing else attached to it, know it's a metallic bond. They're metals alone, not stuck together with something else. Differentiating between ionic and metallic and covalent network and covalently bonded things is key to doing well in this chapter. Thirdly, we're going to go to covalent network. Covalent network things are things like silicon, carbon, silicon dioxide, pure substances usually that are stuck together really good and have a high melting point. Silicon dioxide, of course, is something like sand. Carbon in the form of diamond is a covalent network. Pure silicon usually have really high melting points. They're strong. They're really well stuck together. If you see those types of things, no covalent network. They're kind of rare in the questions, but you've got to be able to differentiate between covalent network, metallic, and ionic. The last one, and the one that we're going to spend 90% of the rest of the time here on today in this, are covalently bonded things. Now, covalently bonded things are all nonmetals stuck together. Covalent bonds, remember that are shared electrons between nonmetal atoms. The other name for these are covalently bonded things are also known as molecular things with covalent bonds. Molecular things with covalent bonds. Therefore, they have intermolecular forces. Therefore, these things have intermolecular forces. Okay? Now, here's the problem. A lot of people get the word inter and intra mixed up. Intermolecular forces means between molecules. Intramolecular forces means inside of the molecule. So for an example right here, in carbon dioxide, which is 2 nonmetals, or actually 2 types of nonmetals stuck together, this bond right here, this double bond, is in the intramolecular force. It's called a covalent bond. It's a double bond, covalent bond. The intermolecular force would be between 2 carbon dioxide molecules. What holds one carbon dioxide molecule to another carbon dioxide molecules? So get these straight. Inter versus intra. Intra means inside, or the bonds that hold the molecule together. Inter means like an internet or an interstate. It connects states, or it connects the world on computers. Okay? So these bonds right here are what we're mostly going to focus on, because these are the ones that are broken when there is a phase change. These intermolecular forces. We don't break the intramolecular bonds right here when we melt, boil, sublimate, things like that. We break these intermolecular forces right here. You have to be able to differentiate between these 4 types. So that's the overview. Now we're going to zoom in, like I said, on these covalently bonded things, and we're going to zoom in on their intermolecular forces, because there are 3 main types of these intermolecular forces, and you need to be able to know what type each type of molecule has. Now still, at first, differentiate between these 4. Once you know it's covalently bonded, which, 80 to 90% of the molecules that we talk about in this chapter are, although they throw some distractors at you in a multiple choice test, you got to be able to differentiate then between these intermolecular forces right here. All right, so let's zoom in on intermolecular forces. Write this down now. This is a new piece of paper. Get it out. Pause the video now if you need to. First, there are things called London Dispersion Forces, LDFs. Sometimes they're just known as Dispersion Forces. Dispersion forces are what's called an instantaneous dipole. And what that means is at one instant in a molecule, we'll use carbon dioxide again for an example, the electrons might be more zoned in this area, so more of a negative here and more of a positive here, and then what they'll do is they'll attract to another carbon dioxide molecule that has a similar thing going, where maybe there's more of a negative here and more of a positive here, and we're kind of attracted between those two things right here. This instantaneous dipole is known as a dispersion force. Now, it might change in the next snap of a second, but during that second, that happens. Size determines how strong these dispersion forces are. The bigger the molecular weight, the bigger the dispersion forces. The more electrons something has, the more dispersion forces you're going to have. Secondly is shape. The longer and more surface area, that a molecule has, the more chance it's going to have these dispersion forces. So we look for long, skinny things. They have more dispersion forces than smaller, fatter things if they're of similar molecular weight. London dispersion forces are not super strong, but they're in everything. They're in everything that's molecular. And molecular, remember, means all non-metals stuck together. The second one are called dipole-dipole forces. Dipole-dipole forces occur in polar molecules. Polar molecules means that there's two poles. There's a positive and a negative pole. And this is because the molecules are asymmetrical in shape. Asymmetrical means when you cut them in half, they're not the same. And cut them in half, they're not the same. So something like this, carbon connected to a fluorine and then connected to hydrogens all around, would be asymmetrical, because if I cut it here, it'd be different on one side than the other. And so therefore this would be a polar molecule with more of a partial negative charge here, more of a partial positive charge, and therefore this partial negative and partial positive would attract to the partial negative and positive of another molecule that's usually the same thing. This is held together by dipole-dipole forces. Now, a special case of dipole-dipole force is called a hydrogen bond. A hydrogen bond is a special case of a dipole-dipole force where hydrogen is connected to an F, an O, or an N. Connected to an F, an O, or an N. So, for example, in the water molecule here, we've got hydrogen connected to an F or O or an N, and we've got more of a positive charge on one side, more of a negative charge on the other. Got more of a positive charge on this side, more of a negative charge on this end, and this dipole-dipole attraction is especially strong because it's called a hydrogen bond, because the hydrogen atom is only composed of one electron. Its electron is ripped away and the nucleus is widely exposed, allowing it to be attracted to this partial negative charge that's on the oxygen right here very, very heavily. Hydrogen bonds are way stronger than just regular old dipole-dipole forces, and that's what makes water stick together really, really well. Those three are the major intermolecular forces for things that are molecular or covalently bonded. These are responsible for the phase changes in things that are molecular. They're responsible for the phase changes in things. Solid to liquid, solid to gas, liquid to gas, and then back and forth. And you need to know the names of those types of changes and then be able to tell which things stick together the best based on their intermolecular forces. So just to give you these really quickly, solid to liquid, of course, is called melting. Solid to gas is called sublimation. Liquid to gas is called boiling. And then gas to liquid is called condensation. Gas to solid is called deposition. And then liquid to solid, backwards, of course, is called freezing. And you might say, hold on. Isn't there a thing where liquid goes to gas that's called evaporation? And you're right. But remember, we're talking about the phase change where the entire substance goes from one phase to the other. This is called boiling, and that's the difference between boiling and evaporation, which we'll get to in just a second. You need to know the names of those and realize that these intermolecular forces are the ones that are responsible for it. The stronger the intermolecular forces, the more these things want to stay in these more condensed phases like solid or liquid. And that's the next sheet. Get a new piece of paper. If you're not caught up with me yet, pause the video now and review it. The stronger the force is, the more they stay in the condensed phases. And the condensed phases are solids and liquids. They're the most arranged and the closest together. Gases are far apart, and so once we break those intermolecular forces, eventually they'll become liquids, and then for sure they'll become gases. It takes a lot of energy to have that happen. But you know, the things with the weakest intermolecular forces are going to end up being way over here by gases. The things with the strongest intermolecular forces are going to end up being down here in the solid area. And this is true for just about everything. So let's talk about those phase changes again. I mentioned before that there's this disconcerting definition that people can't wrap their brain around between the change from liquid to gas. And let's talk about those two changes. There's the thing called evaporation, where at the surface of the liquid, it changes to a gas. Notice it's at the surface only, it changes from a liquid to a gas. If it happens throughout the liquid, then we are having a change that's called boiling. Okay, that's the difference. And we hit that boiling point when the intermolecular forces are weak enough, or the temperature is high enough that the intermolecular forces are weak enough. We've raised the kinetic energy enough, because remember, temperature is directly proportional to kinetic energy. So they can fly from liquid to gas. The faster or more they evaporate, the higher the vapor pressure of the substance, which leads to the definition of boiling. Not only is it throughout the liquid, but the definition of boiling is when the vapor pressure of the liquid is equal to the atmospheric pressure around the liquid. The weaker the intermolecular forces, the higher the vapor pressure. The weaker the intermolecular forces, the higher the vapor pressure, because it's going to go from that liquid to that gas quicker. This also happens with solids too, because solids sublimate. Solids sublimate at any temperature. They change from a solid to a gas. Now, they might not sublimate very much, but the more they do, the weaker the intermolecular forces. This is extremely true with things like, for example, carbon dioxide. Carbon dioxide sublimates right away. Goes from a solid to a gas as long as we're at atmospheric pressure. Phase changes defined. Once again, I went over these already. Solid to gas, sublimation, gas to solid, deposition. Liquid to gas, once again, boiling. Gas to liquid, that's called condensation. And then remember, if it's just at the surface of the liquid going to a gas, remember that's called evaporation. And then liquid to solid, of course, is freezing, and then solid to liquid, once again, is melting. And we could have solid going to gas sublimation occurring. We could have a pressure of the vapor of the sublimated thing as well, which, you know, that leads once again to vapor pressure. These phases can be diagrammed in something called a phase diagram. A phase diagram shows the atmosphere, or the pressure of the substance on one side and the temperature on the other. And there are some special areas of this. This is the solid area of the substance, the liquid area of the substance, and the gaseous area of the substance. And these lines define the barrier between the solid, liquid, and the gas. As we move from solid to liquid, of course, we enter that melting or freezing point. As we move from liquid to gas, we go from that to that boiling point, or where we're doing the condensation point. If it occurs at 1 atmosphere, we're at what's called the normal melting point, right here from solid to liquid. If it occurs at 1 atmosphere from liquid to gas, we're at the normal boiling point. The normal boiling point, where we're moving from liquid to a gas. Eventually, we reach a certain temperature where we reach what's called a critical point. And at the critical point, no matter how much pressure we add to it, the line goes vertical right here. And no matter how much we add to it, you can't make it be a liquid anymore. You get what's called a supercritical fluid at this point. Okay? And then down here is called the triple point. This is where solid, liquid, and gas all are together in one equilibrium. So that's chapter 11. That's kind of a quick overview of the whole thing. But, you know, if you didn't do as well as you wanted to on the test, hopefully that gives you some background knowledge about it as well, and gives you, you know, some notes to refer back to as we go through the chapter 11 test. So pause the video now, and I'm going to go through a couple of these chapter 11 forces, liquids, intermolecular forces, liquids, and solids. Test, pause the video now, and make sure that you have this particular test out, and then just continue with the next video, because I'm going to go over each one of the problems individually, and you can write them down just like I showed you before to make sure that you've got them all correct as we go. So here we continue with the Chapter 11 Fix Your Test. First of all, make sure you've taken all the notes, written them down really neatly on separate pieces of paper. Now we go to this part where you're going to fix each problem you got wrong. First, you're going to write down the number of the problem and the correct answer, and I'm going to do this step by step with you. Then you're going to write down why you got it wrong, not just a made-up reason, but a real reason. What did you not know? And then a reason why you will not get it wrong in the future. What didn't you know before? So pause this video now, make sure that you've got this test out in front of you and your answers so you can know what you got wrong so you can fix them as we go along. All right, I'm going to follow through step by step like that and give you some examples of how the fixing should be done. We'll zoom in on this just a little bit more, and then we're going to go step by step through each problem. It's going to take a little while, but you can skip ahead if you got one right or you understand what's going on with them. First of all, use the answer key below, the phase diagram above, to answer the first 4 questions. If the temperature goes from 10 to 60 at a constant pressure of 0.5 atmospheres, here's 0.5 atmospheres, which process occurs? So we go from 10 degrees, which is right here, and we're going to go to 60 degrees, which is right here. What process occurs during that? So follow this line across, and we cross this line, which, remember, this is the solid area, this is the liquid area, and this is the gas area. So we're going from a solid to a gas, so this answer is A, sublimation. So on your fix-it test, you should write down, if you got this wrong, you should write down number 1, and you should write down the correct answer is A, and then you should write down, why did I get it wrong? I didn't know the definition of sublimation. I didn't know that it was a solid to a gas. I forgot that, or something like that. Okay, there's my reason. And then, why am I not going to get it wrong again in the future? Well, I know sublimation is the change from solid to gas. So I'm not going to get it wrong anymore because I know solid to gas. And the converse of this question would be is if it's going from gas to solid, I know that's called deposition. So if I'm asked about the opposite of it in a future test, I know that that's right too. Skip a line now, and you can go on to number 2. If you got that one wrong, you write that one down. If you didn't, then skip to number 3, and you can write that one down next. But this is an example of what you should write down for each problem to be eligible to take the retake on the test. All right, problem number 2. The correct answer is E as in egg. So I'm going to write down the right answers as we go along here. Number 1 is A. 2 is E as in egg. If the temperature decreases from 100 degrees right here, to 60, okay, at a constant pressure of 1.5 atmospheres, so follow this up here. We're in the liquid area. To 60, we're in the solid area. Which process occurs? So we're going from from liquid to solid, and this is letter E. It's called freezing. Do the same thing now. If you got this one wrong, you can write it down. You can say the correct answer is E, and I got it wrong because I didn't know the definition of freezing. I didn't know that it was going from liquid to solid. I didn't know that it was at 1.5 atmospheres of pressure. And now say why you won't get it wrong in the future. Pause the video now and make sure you've got that written down, because I don't know your for sure reason of why you didn't know that, but that's the definition of going from a liquid to a solid. It's called freezing. Okay, number 3, if the pressure increases from 0.5 atmospheres, right here's 0.5, to 1.5 atmospheres, that's right here, at a constant temperature of 100 degrees Celsius, that's right here. So we're going to start here, and we're going to go up to here. Okay, which process occurs? We're in the gaseous phase, and we're going to go to a liquid phase. We're going to go from a gas to a liquid. So that's called condensation. I forgot to say the answer to this is B, as in Bob. So that's called condensing, when you go from a gas to a liquid right here, from a gas to a liquid. So write that down. Number 3, write down the correct answer is B. The reason I didn't get it right was because I didn't know what condensation was. And now I know that condensation is when it goes from a gas to a liquid, and you can write that a lot neater than I did. Question number 4. Question number 4. Now we're off of that graph. Question number 4, the answer is D, as in dog. The correct answer is the normal boiling point of the substance is approximately, Shoot, we're still on the graph. The normal boiling point. Now, the normal boiling point, remember, takes place at 1 atmosphere of pressure because that's what normal or standard atmospheric pressure is. So we've got a 1 atmosphere right here, and we go to the boiling point. So we want to find out where it changes from liquid to gas. It's right about here, okay? So that looks at somewhere around about 90 degrees Celsius. If you looked at me, I wrote it right here and I dropped it down here and I got really close to 90 degrees Celsius right there. That's the normal boiling point. If you didn't get that right, write it up on the sheet just like I showed you. Write down the correct answer, write down why you got it wrong, and then write down, you know, why you won't get one wrong like that in the future. Then skip a line and go on to the next one. Number 5, the correct answer is B as in Bob. B as in Bob. The melting point of magnesium oxide is higher than sodium fluoride. Explanations for this observation include which of the following? Well, now we go way back to what I talked about before. You've got to be able to differentiate between the different types of intermolecular forces that are going on here. Are they covalent? Do they have intermolecular forces like, you know, like we talked about, dipole, etc.? Are they all non-metals? Or are they covalent network? Do they have silicon or carbon or silicon dioxide in them? Are they metallic? Are they just metals? Or are they ionic? Are they a metal and a non-metal, or a metal and a polyatomic ion? Well, lo and behold, if you look at this, magnesium is a metal, sodium is a metal. Oh, we got a metal with a non-metal and a metal with a non-metal. Oh my goodness, these are ionic compounds. And ionic compounds, remember, are held together by lattice energy. And lattice energy, remember, depends on the charges, Q1 and Q2, divided by D. And the D is the distance between the ions. So you can say for sure it's part 1 because magnesium is more positively charged than sodium, because the bigger the charges, the bigger the lattice energy. They're directly proportional. And then you can also say that number 2 is correct as well, because O minus is bigger charged than fluorine. Fluorine is -1, oxygen -2. 3 is not correct because O2 minus is not a smaller ion than F minus, because if you remember your ionic trends, oxygen and fluorine are right here on the periodic table. If you've got a periodic table in front of you, you can see that oxygen comes before fluorine. Let me see if I can find a periodic table for you here. Here's oxygen on the periodic table. Here's fluorine on the periodic table. And then when you add 2 electrons to oxygen and 1 electron to fluorine, they both look like neon, but oxygen had 2 electrons added to it, so it's bigger. It's bigger. So oxygen would technically, the O2 minus ion right here would be bigger than fluorine. So this one is just false of itself. So write down the correct answer for that, and then write down why you got it wrong, and why you won't get one like that wrong in the first place. If you couldn't differentiate that it was ionic, make sure to say that. On to the next page, number 6. On a mountain top, observe that water boils at 90, not 100, as at sea level. This phenomenon occurs on the mountaintop because the correct answer to this is C, as in cat. This is because the equilibrium vapor pressure equals the atmospheric pressure at a lower temperature. Well, this goes back to knowing your definition of boiling. And the definition of boiling, remember, is when the vapor pressure of the substance is equal to the atmospheric pressure of the substance. And now they put a fancy word into it, in front of it. They called it the equilibrium vapor pressure is equal to the atmospheric pressure. At equilibrium, water vapor pressure is exactly what water vapor pressure is. And it equals the atmospheric pressure, but it happens to happen at 90 degrees Celsius. So you need to know the definition of boiling to be able to answer number 6 correctly. And if you didn't know that, write that down. Say why you won't get one like that wrong in the future. Number 7, which occurs when a substance is converted from liquid to gas at a normal boiling point. The answer to this is D, as in dog, which is 2 and 3 only right here. Okay, when it goes from a liquid to a gas, the distance between the molecules increases. Definitely. Gas is more spread out than the condensed phase of liquid or solid. And number 2, the average kinetic energy of the molecules increases. You increase that phase, or you change that phase, of course you're going to spread the molecules out further. And so the kinetic energy increases because they're going to be moving faster when they move apart. Now, The temperature might not change, but you're adding energy to it, and that energy is kinetic energy at the normal boiling point. The potential energy doesn't increase because, remember, potential energy is just an energy of position, and if you haven't changed the position of the molecules or ions, you've actually spread them apart further. So fix that on here. Make sure that you write down number 7. Make sure you write down the correct answer was D. Why did you get it wrong? Maybe you didn't know what kinetic energy was. Maybe you didn't know the difference between potential energy and kinetic energy. Write those down. Potential energy is the energy of position. Kinetic energy is the energy of motion. And then write down why you won't get one like that wrong again. Pause the video now if you need to do that, so then you can learn from this, and then you can do better on the retake. Number 8. Which of the following accounts for the fact that liquid carbon dioxide is not observed when a piece of solid dry ice is placed on a lab bench? The answer to this is E as in egg. It's because the triple point for CO2 is above 1 atmosphere. And that's true for carbon dioxide. If you know anything about something called dry ice, you know that liquid carbon dioxide doesn't exist on Earth in normal conditions. As a matter of fact, if you've taken a look in your textbook, there's a really nice phase diagram of carbon dioxide, and you don't even reach the triple point until you get to 5 atmospheres of pressure. So dry ice sublimates. It goes from a solid to a gas right away. So if you didn't know that, write that down on a piece of paper, and then write down why you didn't know it and why you're not going to get it wrong in the future. Number 9. The correct answer is E as in egg. What accounts for the intermolecular forces between CCl4 molecules? Now, they even gave you a hint here. They said intermolecular forces. So you know you're in the realm of what we spent most of the chapter on. We're in this area here where we're talking about London dispersions, dipole-dipole, or hydrogen bonds. It's going to be one of these 3. Okay, so what is it? Well, draw CCl4. It's going to look like this. I won't put all the electrons in, but notice it's perfectly symmetrical. Therefore, it's a nonpolar molecule. And the only thing that acts between nonpolar molecules are things called London dispersion forces. There's no dipole-dipole, no ionic, no metallic, no hydrogen bonding, because obviously there's no metals in there, so those 2 are out. There's no H bonding, there's no dipole-dipole, because it's a nonpolar molecule. Number 10. Which explains why the boiling point of HF is greater than the boiling point of H2? Well, once again, boiling points depend on the forces that hold them together. So ask yourself the question right away, is HF and H2, go way to the back to the beginning, ionically bonded, metallically bonded, covalently bonded, covalent network bonded? Which one of these are they? Well, as it turns out, they're all nonmetals, right? So that means they're covalently bonded, which means they have intermolecular forces. So now you're into the realm that we spent all kinds of time on, London dispersion forces, dipole-dipole forces, or hydrogen bonds. And bang, it should just jump out at you that there's a hydrogen connected to a phone, a fluorine, chlorine, or a fluorine, oxygen, or nitrogen, and therefore it's going to be hydrogen bonded to one another, which is a super strong intermolecular force for the size of the molecule. Hydrogen, of course, are just bonded by London dispersion forces, which are relatively weak, especially for this really small molecule. So the answer to 10, I was supposed to give the answer first. The answer to 10 is A as in aardvark, because it's hydrogen bond. 11 is, the answer is D as in dog. Which liquid has the highest vapor pressure? Now, vapor pressure means that it's going from a liquid to a gas at this temperature, just on the surface of the liquid. So it's the one with the weakest intermolecular forces. So you've got to go through and look through here, and you've got to find out which one has the weakest intermolecular forces here of all the ones. Am I on number 11? Yeah, of all the ones together. And let's see, we chose D as in dog, which is CH2Cl. And then this one would have some dipole-dipole forces, but and it would also have some London dispersion forces because it would be an asymmetrical critter. You could maybe make a little bit of an argument that this guy right here would also have dipole-dipole forces, and therefore be also have a fairly high vapor pressure, but notice it has more chlorines than this one does, so it has a higher molecular weight, and since it has a higher molecular weight, it's going to stick together a little bit better due to its London dispersion forces. Water and H2O2, of course, are going to be hydrogen bonded together, so those are going to stick together a lot better. And CCl4 is really big because it's got 4 chlorines around, and even though it's nonpolar, it's going to have really strong, much stronger London dispersion forces because it has about 71 grams per mole more mass due to having 2 more chlorines than this critter right here. So this is probably the trickiest one we've encountered so far on the test, but D would be your best answer for that. Pause the video now and write down why you got it wrong, why you won't get it wrong in the future. Number 12. Correct answer to number 12 is B as in Bob. Which statement is true about the critical temperature? The critical temperature is the temperature above which the liquid phase of a pure substance cannot exist. Remember, it becomes a supercritical fluid above that point. Supercritical fluid, and I think I had a little picture of this earlier. And so you can't, no matter how much pressure you put on it anymore, it cannot become a gas anymore. It just goes vertical right here, and no matter how much you pressurize it up this direction, you're not going to make it go back this way at all. It's just going to stay as what's called a supercritical fluid, or kind of in the semi-gaseous phase there, and not become a liquid. Number 13, which choice represents intermolecular forces listed in order from strongest to weakest, assuming now, and this is a tricky part about this number 13, this is probably the second trickiest problem, that the molecular weight stays relatively the same. This is D as in dog, saying that hydrogen bonds are the strongest, dipole-dipole attractions are the next strongest, and dispersion forces are the weakest. And of course, this assumes that the molecules you're looking at aren't massively different in size, because if you get a much bigger one, 80, 70, 100 molecular weight difference, of course, dispersion forces are going to take over. Pause the video now. If you get that one wrong, change it. Number 14, arrange the following order, increasing boiling point. So now you go way back to the beginning of my talk, and you have to be able to differentiate between the forces that are here. There's an ionic one in there. There might be a metallic one in there. There might be a covalent network in there. And then there's some of the regular covalent that are nonmetals stuck together. So they use dipole, London dispersion forces, things like that. Let's differentiate between those before we do it. This one here, NaCl, ionic. Going to be super strong stuck together. This is 2 nonmetals stuck together, so it's going to be things called London dispersion forces stuck together because it's nonpolar. This guy going to have some hydrogen bonding in it. It's all nonmetals, but hydrogen bonds, remember, are stronger than London dispersion forces. And this guy's going to have some hydrogen bonding. Oh, no hydrogen bonding. I'm sorry. It's got hydrogens connected to carbon right here. And then it's going to have a chlorine on it, giving it a dipole moment. So it's going to have some dipole forces with it as well. So the correct answer to number 14 is B as in Bob-Reno. And this would be the weakest, CO2, just London dispersion. CH3Cl, that's going to be this critter right here, which has dipole forces. And then CH3OH, that's going to be a hydrogen bonded thing. And then ionic, of course, they're going to be the strongest thing with the highest boiling point. Pause the video now, write down why you got it wrong, write down why you're going to get the next one right. Number 15, the answer is B as in Bob. It relates to this graph right here. It says the substance that has normal freezing point. Well, that means that this is the solid, this is the liquid phase, and then the gaseous phase would be up here. It tells us that up here, that graph shows a pure substance at adhesion constant rate. The substance changes from a solid to a liquid to the gas phase, okay? So right here we're going from a solid, so right here is where we have the normal melting point, and then we're going to change it into a liquid, and then this is where we're going to have the normal boiling point happening. So the time that it says the normal freezing point would be where it goes from a liquid to a solid. That would be right here at T2, which is B as in Bob. The next question also uses this diagram. Number 16 says, which best describes what happens to the substance between T4 and T5? The correct answer to number 16 is A, as in aardvark. The molecules are leaving the liquid phase. So between T4 and T5, now remember we're going to look back at the diagram. T4 and T5 are right here, and this is on the flat part of the graph. We're increasing in time, and therefore also in energy that we're adding, and then we're not increasing in temperature. So this is where the phase change is occurring from liquid to gas right here. And so when we're going from liquid to gas, substances are leaving the liquid phase and going into the gaseous phase. Number 17, the correct answer is D as in dog. And the reason it's D as in dog, it says the phase diagram above appears some X is shown. The temperature of the sample of the pure X is slowly raised from 10 to 100. 10 right here to 100 right here at a constant pressure of 0.5. So we're going to go from here at 10 to 100 right here. What is the expected behavior of the substance? The answer is D. It sublimes to vapor at an equilibrium temperature of about 20. And you can see right here, it crosses this line right here at about 20 degrees Celsius. And then it continues in its gaseous phase over here, because remember, this is the solid, this is the liquid, this is the gaseous phase right here of a phase diagram. Pause the video now, write down why you got it wrong and why you will not get it wrong in the future. Number 18, the answer is B as in Bob, which describes the changes in force of attraction that occur as H2O changes phase from a liquid to a vapor. The number of hydrogen bonds between H2O molecules are significantly reduced. And if you remember watching the video in class about H2O, they had a nice little model representation about how when you go from a liquid to a vapor, some of the hydrogen bonds, or all of them pretty much, are broken, and these allow the water molecules to fly off by themselves and not be attracted to each other very much at all. Because in the liquid and the solid phase, of course, they're attracted much, much more strongly. That is why they're called the condensed phases of matter. Number 19, the answer is C as in cardboard. The best explanation for the fact that diamond is extremely hard is that diamond crystals are giant molecules in which each atom forms strong covalent bonds with its neighboring atoms. Going back to the very beginning of my talk now, one of the things that holds things together are called covalent network, and I said those are super strong bonds. Pure carbon, like diamond, for example, are held together, and they have really high melting points, and they're strong intramolecular covalent network bonds. Number 20, 20 is A as in aardvark. The boiling points of the elements helium, neon, argon, krypton, and xenon increase in this order. Which statement accounts for this increase? Well, remember, these elements are just simple atoms, and so all they've got is electrons. They're not polar, and they're non-metals, so the only thing holding them together are London dispersion forces. And so the London dispersion forces increase because you have more electrons in them. If you didn't know that, you could take a look on your periodic table, and you could see that helium, neon, argon, krypton, and xenon increase in that order because they have a larger molar mass, and therefore they have a larger number of electrons around them. Number 21, correct answer is A as in apple. Which will not hydrogen bond? Remember, to have hydrogen bonding, you have a hydrogen connected to an F, an O, or an N. Hydrogen connected to an F, an O, or an N. So we've got right here this guy with no hydrogen in it. So there's no way that you can have a hydrogen connected to an F, an O, or an N. Here you can see you got a hydrogen connected to an oxygen. Here you got a hydrogen connected to nitrogen. Here you got a hydrogen connected to an oxygen. And here you got a hydrogen connected to an oxygen as well. They actually write this HClO, but it's actually like this when you do the Lewis electron dot structure, ClOH, because O's in the middle. Number 22, which of the following statements is not consistent with the crystal properties of the substance? The correct answer in number 22 is C as in cardboard. Aluminum is used to cut glass. Aluminum is not used to cut glass. You can't cut glass without anything except like diamond. That's super duper hard. Aluminum's not super duper hard. Tungsten's a metal. It can be drawn into thin wires. Silicon carbide is used to grind parts into shapes. That's another one of those that's a network covalent thing, super strong bond. Graphite is used to lubricate locks. That's very true because it's very slippery over itself. And MgF2 shatters when dropped. That's an ionic compound that sticks together really good. If you didn't know those characteristic things, they often ask 2 or 3 of those questions on the AP exam. You know, that's just things that they're like, oh, you've been around chemistry for a long time, so you know some stuff about some stuff. And I can't predict what stuff about stuff you need to know, but I can put stuff in front of you, and I can put Chapter 11 in front of you and dive into that. You'll find a bunch of it. Number 23, the correct answer is D, as in dirigible, which occurs at point X right here. Well, the correct answer is that point X, which occurs at point X. D2, only the liquid exists, the solid exists. Do I have the right answer there? I looked at the wrong one. 23. Should be E as in agavist. E. 1, 2, and 3, because this is called the triple point. And at the triple point, you have a solid, a liquid, and a gas at the same time, because it's the joining of the solid, liquid, and gas places. Sorry, I had the wrong answer there. I looked at the wrong answer key place. But that's 1, 2, and 3, and that's E as in egg there for number 23. Fix that if you got that wrong, just like I did. And then you can say why you will not get it wrong in the future. I guess if you just looked at the wrong answer and filled in the wrong bubble, that I guess is legitimate, but let's hope that's not true. Number 24, the answer, I want to make sure I get this right now, is A, as in aardvark, above which temperature will no amount of pressure liquefied carbon dioxide gas refer to the phase diagram above. So now we're looking where you can't liquefy it anymore, so this is going to be called the critical point. So above here, right above here, it goes vertical, and we're at what's called the critical point. So that's point Z, as in Ziggy. And so, I need to know a temperature for that. So Z right here occurs at 31 degrees C, right down here. You can see that, 31 degrees C. Follow that up. Z. 31 degrees C is right here. 25. Why does liquid carbon dioxide not exist on Earth under normal conditions? Refer to the phase diagram on the previous page. Well, liquid carbon dioxide does not exist under normal Earth conditions because if you look right here, to be a liquid, you have to be a liquid right here. You have to be above 5.11 atmospheres. Standard atmospheric pressure on Earth is 1 atmosphere. Hey, remember how I talked about a phase diagram for carbon dioxide? You could go back and you could use this on a question that you had before, because there was a question before about why don't you see carbon dioxide, liquid carbon dioxide on a lab bench? Well, at 1 atmosphere on a lab bench, it just goes from a solid to a gas. That's because the trouble point isn't even until you get 5 atmospheres, which is way above standard atmospheric pressure. So the correct answer, I forgot to give that to you right away. Correct answer for number 25 is D, as in dog. Carbon dioxide only experiences approximately 1 atmospheric pressure here on Earth. You'd have to have a lot more pressure, and we'd be squished a lot here on Earth if that was true. Number 26, the phase diagram for a pure substance is shown above. Which point on the diagram corresponds to the equilibrium between the solid and liquid phases at the normal melting point? Well, the normal melting point is when we have normal or standard atmospheric pressure. And remember, this is solid, this is liquid, this is gas. So follow this over for the phase interchange between solid and liquid. So the correct answer for 26 is C as in cat, which is C as in cat right there. The last one. Pause the video now and fix any other ones that you need to. The cooling curve for pure substances changes from liquid solids below, shown above. The solid and liquid coexist at, and this is the liquid phase up here. This is the solid phase right here, and here's where the phase change takes place. Q is called a supercooled liquid, and then between R and S right there is where we have Q, R, and S is where we have the phase change going on, and this supercooled liquid right here starts its change from liquid to gas, and so the correct answer is C, as in cat, where all points on the curve between Q and S occur, right here along the way between Q and S. That's where the substance that can coexist as a solid and a liquid. Excuse me. So that completes the test. Go through that now and remember what you need to do for each one. Fix each problem you got wrong. Fix each one that you got wrong. and then write down the correct answer, the number of the problem, the correct answer, why you got it wrong, the real reason why you got it wrong, why you will not get it wrong in the future, and what you didn't know. And it might be stuff that, you know, you just didn't know. Maybe I didn't tell you. Maybe it was something crazy like, hey, I had no idea that silicon and carbon went together to grind metal pieces. That's fine. Write that stuff down. Now you know it. Now you're ready for the retake. Thanks for watching. Hope you do better in the future.